Right, so one of the questions we might ask in isotope geochemistry is how we can actually get quite large differences in the isotope ratios recorded in different things we find around the Earth, so between maybe the ocean and ice sheets here, when actually some of the processes or the equilibrium fractionations that can separate the two isotopes one from the other are actually relatively modest. So you can see this graph is showing the isotopic composition of water in the ocean through time, starting maybe 150,000 years ago, moving to the present over here. There are small differences. We can see that the last glacial maximum, the isotopic composition was maybe a little bit heavier in the water in the ocean, but not changed much from the modern value. In contrast, we can look at ice sheets, and we can see that first of all, there's a huge difference between the water that's ultimately the source of the water in ice sheets, so it evaporates over the oceans, and it precipitates out the snow over the ice sheets. And something is causing these to be very much lighter in their isotopic composition, so up to maybe 5% enriched in the lighter isotope O16 over the heavy isotope O18. So one thing we might want to think about is how do we explain that? These large differences that we can kind of produce by processes on the Earth. So these are much larger than the isotope fractionations from a single kind of fractionation between two phases. So it turns out that even if we have a small fractionation, we can actually, if we separate the two phases which we've fractionated the isotopes between, maybe either water and water vapor, or water vapor and then the condensate liquid, there might be some isotope fractionation between those, but if we continually separate our reactants from products, in this case, and then continue that process of then producing more of the product by maybe condensing more or evaporating more, we can do this process called isotopic distillation, sometimes called Rayleigh distillation. And what we're going to do now is basically go through the process of explain how we can start. If we start out with a fraction of something that's remaining, so we start out here with all of our reactant remaining, and if we produce a fractionation from that, so if we produce something that's maybe isotopically heavy, what gets left behind progressively gets lighter and lighter and lighter and lighter. So we're just going to go through and explain how we can do that. So the example we're going to use is the evaporation of water. So because there's a difference in bonding environment between the water and the water vapor, then there should be some isotopic difference between those two phases if we allow them to equilibrate with each other. And it turns out that water, the bonding environment of oxygen in water is slightly stronger than the bonding environment in water vapor, and this is largely due to the hydrogen bonds that form between water molecules. But it doesn't really matter what's causing the difference in bond strength in this case. We just kind of take it as read that the fractionation between water and water vapor means that the liquid phase is enriched in the heavier isotopes by around 9 parts per thousand. It's actually in reality, in nature, that fractionation is slightly larger because the process is not always at equilibrium, so there may be a small amount of kinetic fractionation then as well, but between 13 and 9 per mil is what we might expect in the environment. So if we have some water and we evaporate that water, the water vapor would be expected to be approximately 10 per mil enriched in the lighter isotopes. So what we're going to do now is see what happens if we continue this process and continually remove the thing that we're producing by the evaporation or condensation, to try and explain how we get these differences between these ultimately the ocean from which everything is evaporating from. Okay. Now, if that was all that was happening, if we evaporated the ocean and then formed some some water vapor from that, we might expect that to follow and be of a composition approximately 10 per mil lighter. And if we then precipitated all of that out, then that's what we would expect to get. But we can see here that the actual precipitation is in fact much lighter than that kind of initial fractionation between water and water vapor. So you've got to explain why that might be. So we're going to look at now at using condensation to an example of the process of continual removal. So imagine now we start out evaporating some water, we produce a cloud of water vapor, or just not necessarily a cloud, but a box, let's say, full of water vapor, and then from that water vapor we condense out some liquid. The liquid that's condensed from that water vapor will be isotopically heavier than the water vapor, so if it's at equilibrium it should be the same as the water that it initially evaporated to form the water vapor. But if we think about what's happening at any one point during this process of condensation, so we think about the different isotopes separately now. So if we think about the O16 water molecule and the O18 water molecule, and we assign that kind of the amount of this water is A and the amount of this water is B, then the rates of condensation are effectively just the rates of removal of or the rate of change of that total amount of vapor that we have. So at any one point, the rate of condensation here is the rate of change of the amount of water vapor we have. Okay? And similarly for the lighter isotope, we can have a rate of change of or rate of condensation of the lighter isotope, in this case the heavier isotope, sorry, and that's similarly basically the rate of change of how much of vapor we have and how that's changing through time. So we can think about the fractionation of the isotopes being just the difference or the ratio of these two condensation rates. So if both isotopes condensed at the same rate, then there would be no fractionation between the isotopes. But the heavier isotope is likely to condense a little bit more rapidly, okay, because it prefers being in the liquid phase rather than the vapor phase relative to the lighter isotope. So we could express some fractionation factor as just the ratio here of the rate of condensation of the heavy isotope over the rate of condensation of the lighter isotope. So we can plug in these descriptions of what the actual rates of condensation, that is just the change in the amount of any of the isotopes per the amount that we had at any one point. And we can then get an equation like this, which gives us kind of essentially the fractionation factor expressed in terms of the removal of each of the isotopes relative to the amount that was there at any one point. We rearrange that equation to get an equation like this, and then we can integrate that, because what actually we're interested in is not the rates of change of these different isotopes, but we're actually interested in the amounts of each isotope at any one point, or the amount of isotope that's being removed at any one point, because if we can then effectively then work out the ratio of those, we can work out the isotope ratio of the product or the reactant that's remaining at any one point. So to go between rates and amounts, we have to integrate. So to integrate, we get an equation like this down here, which obviously has these constants of integration in, which we can set to the amount of stuff that is remaining or was originally in our kind of imaginary box of vapor containing all of the stuff that we'd evaporated initially. So that then gives us this equation down the bottom here, which is very nice, which we can rearrange to give this equation here using just the rules of logarithm. So actually log A minus log A naught is essentially log of the ratio of those two amounts. So that can be rearranged to give this. Just kind of remove those logs. Now, the next bits, or all these bits of manipulation might seem like they're seemingly arbitrary and we're kind of doing them for no kind of reason, but hopefully you'll see that this is to effectively produce something which allows us to express the isotope ratio in terms of something we can actually measure. So if we move on here, we can seemingly divide by A over A naught, and that gives us this, because dividing by something is the same as timesing by it to the power of -1, which is what we're kind of doing here. Gives us this, which is now, I guess we could have plugged in the F up here, but actually this A over A naught, because most of the oxygen in water is going to be O16 rather than O18. We can approximate the fraction of all of the water that is remaining as the fraction of the O16 which is remaining. So that's an assumption we make here. So F now is effectively A over A naught, or the amount of water remaining in the vapor phase divided by the amount of water in the vapor phase that was originally there. So this is kind of starting to look like something useful. So we've got something that expresses the fractionation factor between two phases and the amount of basically condensation that's happened, and the isotope ratio that we have produced at any one point relative to the isotope ratio that we started with. Okay, so this is quite useful, but we can kind of add things, or basically start to make this into something that may be a little bit more familiar. So if we -1 from both sides to get this, so this is now effectively the same as expressing it like this. And then if we times both sides by 1,000, we get an expression over here like this. So now we have, hopefully you might remember this from the introduction to the isotope geochemistry video, but effectively we've got something that describes the isotope ratio of whatever is being removed or being condensed relative to the initial composition expressed in this per mil notation. Okay, so basically in the relative difference in isotope ratio in parts per thousand. Okay, and that can be expressed in terms of this equation here, which has the amount of condensate that has happened and is got something about the fractionation factor in. So this is useful because this value here is effectively the difference in isotope ratio between the starting composition and the composition that happens to be condensing at any one point, expressed in per mil notation, which is something that we can actually measure. So that's this thing at the top here. So what this expresses is this reactant, what's being produced at any one point. So that's this blue curve down here. So what this effectively means is if we start off with say some water vapor that has got an isotopic composition of 0. So this is the difference in isotopic composition in per mil notation relative to the starting composition. So that's by definition going to be 0 to start off with. And then we condense some water from that. That would be of this composition up here. And then if we remove that condensate from the system, if we didn't allow it to equilibrate back with the gas, if we basically allowed that to condensate out of our imaginary box of water vapor, then we'd have removed from our system something that's isotopically heavy, which means what's left behind must get lighter in composition. So if you remove heavy isotopes, whatever you're left with is going to get lighter and lighter and lighter. And that's what happens as we progress along this kind of fraction of what we started with remaining. Our water vapor gets progressively enriched in the lighter isotopes as we're removing at every point along here. We're removing stuff that is isotopically heavy relative to the water at any one point. So when we get to very low fractions of the water vapor remaining, we've actually can drive that water vapor to very, very light values as we've removed all of these heavier isotopes as we've as we've done that condensation. So just to quickly explain the red lines on here, this is what would happen if we started at the initial point here where we had a thing full of water vapor, and we started to condense the water out of that. But instead of removing that condensed water vapor, or condensed water, we allowed it to effectively stay in equilibrium with the remaining water vapor. So at the end of the experiment, if we started at this composition, if we condensed everything out, then everything we condensed out must be the same composition that we started with. Okay, because if you start with say all of the isotopes, the heavy isotopes and all the light isotopes, if you condense that all out, then you must end where you started, because you haven't lost or gained any isotopes. So this is what the red lines on here represent. At any one point, the condensate would be of this composition, and the water vapor remaining would be of this composition. So the difference between the blue curves and the red curves are effectively the difference between an open system where you condense the water vapor and then you take it away and you don't allow it to interact or re-equilibrate with the water vapor. Whereas the red curves are if you have a sealed system and you condense out the water, but you allow it to equilibrate back with the water vapor. So that's these guys. So this is kind of what might be happening in the Earth system. We start out with the ocean, and that might have an isotopic composition that's near 0 parts per thousand difference from the standard, which in this case is standard mean ocean water. So by definition, the ocean is quite often 0. Then some water evaporates from the ocean, and that will be isotopically lighter. So it'll have an enriched in the O16 over the O18. So it'll have a negative delta O18. Now, at some point, some of that water vapor will precipitate out in the form of rain. Now, that rainwater, as it condenses, that condensation process will preferentially remove heavy isotopes from this cloud into rain. And you can see that the rain that falls out of the cloud is indeed enriched in heavier isotopes relative to the water vapor. So we go from minus 13 to minus 3, so that's getting heavier. But this will leave the cloud that's left behind, so not all of the water vapor rains out in one go. So whatever water vapor is left in the atmosphere will be enriched even further in the lighter isotopes. So we've gone from a minus 13 to minus 15. So then when that water vapor in the atmosphere rains out again, okay, it'll still be the same offset between the atmospheric composition and the rain, but the rainfall will be progressively enriched in the lighter isotopes as we go through this process of removing the heavy isotopes every time it rains. So this is perhaps one of the explanations, or is one of the explanations, why the snowfall over the polar regions is so much lighter in its isotopic composition than the ocean that the water originally evaporated from. Because what would have happened is that the ocean composition would be somewhere up here at 0 per mil. Then some of that evaporates, maybe 10 per mil. So we've got the water vapor directly over the ocean might be somewhere at this value here. Then some of that will rain back down into the ocean, okay, removing isotopes of this value near 0 again. So anything that's left in the atmosphere will be progressively enriched in the lighter isotopes. So the delta 18 will become more and more negative. We have then more rain from the atmosphere that will remove isotopes that are 10-ish per mil heavier than whatever the atmospheric vapor composition is, removing it further down here. So actually, the snowfall over the polar regions, although it's kind of ultimately come from evaporation from the ocean, it's been processed so much in the atmosphere by progressively raining out almost all of the moisture that originally evaporated. Only a tiny fraction of the original evaporated water is left. That leads to the isotopic composition of the ice sheets being very much enriched in the lighter isotopes. So you can think of how far you go down in terms of this enrichment in the lighter isotopes is a function of the distance. Perhaps the atmosphere has transported that water vapor over since it was evaporated, or the amount of isolation from the ocean. So as an air mass moves from the oceans over the lands, it'll get progressively lighter and lighter and lighter and lighter as more and more rain falls out of that cloud. So you can see that the Antarctic isotopes here are a little bit more negative in terms of their isotopic delta values than the Greenland ice core up here, and that might be because the moisture that ultimately gets to Antarctica, because Antarctica is so kind of atmospherically isolated from the oceans due to the atmospheric circulation going kind of whizzing around it, then only a tiny fraction of the moisture that evaporates from the ocean actually makes it to the Antarctic continent, whereas a slightly larger proportion makes it to Greenland, which might explain why Greenland ice core is slightly more enriched in the isotopes, in the heavy isotopes, relative to Antarctica, but still much lighter. So actually we can see what the effect of that is on the ocean remaining. And I've just changed the ocean composition here in green to a second scale over here. So I've effectively made the scale 10 times as big. So we can actually now zoom in and see that there is actual variation on glacial interglacial cycles of the ocean composition. At present, we're approximately at 0 parts per thousand, different from the ocean by kind of definition. But at the last glacial maximum, we were maybe 1.5 to 1 parts per thousand enriched in the heavy isotopes. So one of the potential explanations for this is that during glacial periods, around this time here, ice sheets were much bigger. Okay, and those ice sheets would have had these lighter isotopes in them. Okay. So these lighter isotopes, if we're removing lighter isotopes and storing them up in ice sheets, that means the remaining ocean left behind has got to be must be therefore enriched in the heavy isotopes, which effectively remain in the ocean after evaporation. And we can see that the difference here is actually very small. It's only kind of maybe one and a bit parts per thousand relative to the fractionation between the ocean, which is maybe near 0, and the ice sheets, which are maybe somewhere between -40 or minus even 60 per mil in some places. And the reason we only see this small change in the ocean is because the actual amount of water in the ocean is vast compared to the amount of water that was stored up on ice sheets, even though the ice sheets themselves were very, very big. So that this somewhat small change in the ocean composition is due to these very large isotope fractionations, which you get through this distillation process in the atmosphere, causing snow to be isotopically very, very light, and then are storing large volumes of that snow on land in ice sheets, which then forces the remaining kind of budget of isotopes that are left behind in the ocean to become heavy during these glacial periods. Right. So hopefully this has helped explain some stuff about how we can get big isotope fractionations. Bring that back. How we can get big isotope fractionations between water and ice sheets, and also how those continental storage of isotopes during glacial periods can change the composition of the remaining ocean.